share the screen. That's the schedule here. This is the November 17th, 2025. That's 9:42 a.m. Pacific Standard Time. And let's see, when is going to be our third exam? Our third exam is going to be December 3rd. Then December 15th, we have our final exam right in here. Okay. And more people coming. Okay, so I look at the grades of your second exam. Okay, I look at the grades of your second exam. Okay, and what I did, I adjusted it. So you'd get a larger, higher grade. Okay, so just check in a higher grade in percentage wise. Okay, percentage wise. So just check your grade there, and hopefully, okay, that be enough to help you out. And adjusted to help you, right? I adjusted to help you. So you'd get a higher grade. I had a higher grade percentage wise speaking. Okay, so just check. Just check your. Just check your exam 2 grades in Canvas.
Professor, for exam 2, did you say you posted the grade for exam 2 on Canvas?
Yeah. Did you see that?
I do see it, but on my end, it just says here like the instructor has not posted the grade. So
Really?
yeah, I don't know. Because I only see the score that I got for the exam after I finished it. Is that the
Oh,
one
really?
you're referring to, or are you talking about a different one after, since you said that you adjusted?
Do you have the choice? Do you have the option to display the grade of your exam in a percentage there in the screen?
On the screen?
Yeah, check. There is a. I cannot display it the grades here in my screen, right? To show you how to do
Oh,
that. But if you go in the three dots of the exam, for
mm-hmm,
instance, exam 2, right? There is an
mm-hmm.
option to display it in a percentage wise
Wait, so do I go
instead
to
of,
exam 2 and then
yeah,
press the
for the
three
exam 2.
dots?
Yeah, for the exam 2.
Okay.
See, there's an option there to display it. Let me double check that. Let me start sharing the screen. Let's see. Let me see here. Yeah, next to the exam 3, there are three dots in the vertical direction, right? Let's see. At the very when you click the three dots at the very, let's see. Maybe it's enter grade as percentage. Yeah. In my case here, the grades are displayed as a percentage. In your case, it's displayed in points or in percentage?
Mine's in points.
In points, right? Huh. Yeah, I need to talk to Canvas support about that. Okay. Your points didn't change. That's true. But what changed was your percentage. Okay. So you should see the points. You should see the points that you got in the exam. That didn't change. What changed was the percentage. Okay, was the total points of the exam. That's what changed. So I will check with Canvas to see what's going on with Canvas support. But I'm also having a difficulty here on my side. Okay, And but just if you do you see exam 2, right? There in your grade.
Yeah. I
Do you
did
see
test
the
the raw. I did see it.
do you see out of X points?
Yes.
How many points out of let's say
20. It says here out of 25.
yeah, okay. See, that's the point that I changed. It was initially 28.5, and then I adjusted the grade of each some of the questions to help you out in the
Um,
okay. And because
okay.
of that, your percentage grade increased. Okay,
Okay.
everybody's percentage grade increased.
Okay.
But
Got
but
it.
it looks like we are having some difficulty here in Canvas. I'm going to consult with Canvas support to see what's going on. And I do not know why it's not displaying percentage there on your side. You should be able to see that, but for some reason you're not. Okay, but that's the announcement that I want to make. Okay, I look at the grades of your second exam and I adjusted it to help you so you get higher grade percentage wise. But don't forget percentage wise. Your grades in point, your grade in terms of points did not change. Okay, what changed? What changed was the total points of the exam. Yeah, that's right. Okay. 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 So there's one more student here trying to get in. Now let me go back sharing the screen. Okay, and that's the screen. Let me do something else. Hang on, let me stop sharing again. I don't want this screen here to accidentally display there for you. Well, uh-huh. Okay, now I can share the screen with you. Now another student is coming. Let's see here. Okay, there is a student trying to come in. Okay, good, Jason. Now let's see where we stopped. We stopped. We're covering potential energy. There you go. That's chapter 6, okay? Chapter 6. Let's see how I'm going to 6.1. Ah, working kinetic energy theorem. We covered the gravitation. We covered gravitational potential energy as well. So we can both face that. I came up with a table. And conservation of mechanical energy is a straightforward consequence of the work kinetic energy theorem and the definition of potential energy. Okay, so here we go, conservation of mechanical energy, right? So I thought about that, right? And it's just a consequence. 6.5 is just a consequence of this definition here. Ay, 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 ay. I, and now it's stuck here. Yeah, see word not responding. Patient. Okay, good. Now it's finished. Okay, what you see right in here, consequence of 6.2 and 6.3. That's what it is. And we're going to do some examples so you can understand better what it's all about, okay? And I'm gonna do the following. Instead of 6.1, 6.2, why don't we do like, that's okay. Let's do it. Leave this way. Okay, and I came up with this table. Right in here. This table of the potential energy of different types of forces, of different types of conservative force. Okay, so let's not forget, potential energy is associated only with certain types of forces. Okay, and this type of force, the conservative force, the conservative force. Not all forces have a potential energy associated with them. Okay? In particular, the non-conservative forces. The non-conservative forces do not have a potential energy associated with them. And what you have here are the conservative forces nearby the Earth's weight near the Earth's surface, nearby Earth's surface. The weight is simplified and it becomes mg, right? But at any point distant from the center of the Earth, we have that the force is given by this relationship that you see right in here. So what you see right in here, don't forget, is an approximation of what you see right in here, okay? The corresponding potential energy, which is a scalar quantity for the weight nearby the Earth, is mgy. And the corresponding potential energy for the universal law of gravitation is going to be something like that. There is a negative sign here. There's a negative sign here. For the elastic force, which is minus kx, right? A vector. The potential energy is half kx squared. And for the electric force, that has a functional relation very similar to the functional relation of the universal law of gravitation. The potential energy is going to be also similar to the other potential energy. The only difference is in the sign. The only difference is in the sign. Okay. But you know, this potential energy here we're gonna cover with more detail in physics 7. Okay, and let me get to now going back to the work kinetic energy theorem, right? It's not difficult to memorize the work kinetic energy theorem. It's a very important type of theorem, a very important result. So here we go. I am going to work done by the net force is the final kinetic energy minus the initial kinetic energy. That's how we formulate the work kinetic energy theorem. But the work of the net force is also equal to the work of the conservative forces plus the work of the non-conservative forces. Okay? Net force, right? Conservative work done by the conservative force plus the work done by the non-conservative forces. But let's not forget that the work done by the conservative forces, by definition, right? By definition, the work done by a conservative force is minus the initial potential energy plus the final potential energy. Potential energy is minus the work done by the, let's see here, no, sorry, I messed that up, okay? I just changed the order, I didn't change the sign. So how is here you go, it's like that, minus, here you go, minus final potential energy minus initial potential energy. That's what it is. Okay, and then what we end up getting is a plus sign for the initial potential energy and a minus sign for the final potential energy. Here you go. Minus sign for the final potential energy and a plus sign for the initial potential energy. And we define this way because, because of the final result, right, that you saw before, which called the conservation of mechanical energy. So here you go. I'm going to substitute that right in here. I'm going to substitute that right in here. Right? And then I covered that before, right? But I'm reviewing that so you can here you go. What I'm going to do now, I'm going to put this equation in a very intuitive way, in a way that's very easy to memorize. Okay? That's I'm gonna pass everything that's initial, it's gonna be on the left side. Okay, the negative kinetic energy, initial kinetic energy becomes positive, and the negative potential, and everything that's final goes to the right side. Consequently, the negative potential, final potential energy becomes positive. Okay. And now this term here that you see right in here, we call it mechanical energy. Okay. The term, the summation, the sum between potential energy and kinetic energy, we call mechanical energy. And we abbreviate by the letter E. Consequently, this equation now becomes initial mechanical energy plus the work done by the non-conservative forces is equal to final mechanical energy. If the work done by the non-conservative forces, can be ignored, let's say not can be ignored, but is negligible. In many cases, it is. Then the above equation becomes initial kinetic energy equal to final kinetic energy. And that's what we call the conservation of energy. The equation for the conservation of the equation for conservation of mechanical energy. It's not a law, okay? Not in this sense. Carlo is trying to get in, right? Equation for conservation of mechanical energy, right? And I'm going to write that in terms of potential energy and kinetic energy. And that is exactly 6.5. We for kinetic energy, okay? That's exactly 6.5. Let's do some examples. To come up examples. Examples are the best way of understanding all this theory that seems to be so abstract. By the way, can you hear me? It looks like I have lost my internet signal momentarily.
Yeah, I can hear you.
Oh, okay, good. Okay, thank you. I got a message here from Zoom that my internet signal was unstable. So I just want to make sure that you can hear me. Now I'm trying to get Carlo here is trying to. Okay, example. I'm going to show you an example that can be solved either using the argument of forces or the argument of conservation of energy, okay? So you're at the top of a building of height h. You release a small stone from the top of this building. When I mean release, I mean the initial velocity is going to be 0, okay? What's the final velocity of the stone just before impacting the ground? Okay, it's possible to do that in real life, okay? It is possible. Let me write it down. Ignore, see, I am neglect the effects of air resistance. Air resistance, which is a non-conservative force. A non-conservative force. Okay? So you can do this experiment in real life. Okay? In real life, you can do this experiment. You go to the top of a building and release a small stone from the top of the building. And the moment you release, you start timing how long it takes for the stone to impact the ground. Okay. When you see the stone impacting the ground, you stop your clock. Okay. If you know the height, right, of the building, you'd be able to find the velocity, the final velocity of this object. Okay? There are two ways, solution. There are two ways of solving this problem. Either using kinematic arguments, right? Kinematic arguments, or using the equation for conservation of energy. Let's see here. I want to illustrate that. See if we have an illustration here. Right in here. View. Grid lines. Good. Looks better, right? We have this conservative force that is accelerating my stone, my object. It's going to impact when it reaches the floor. Okay, let's see if I have a better drawing here. Yeah, okay. No, I don't have a better drawing. So the way you do is like that. The way you do is like that. The initial mechanical energy here at the top, which is potential energy plus kinetic energy, must be equal to the final mechanical energy at the bottom of the building. Okay? Using the equation for conservation of energy. So since we are neglecting the effect of air resistance, comma, the work of the non-conservative forces can be neglected as well. And we have the previous equation we derived. Yeah. Initial potential energy plus initial kinetic energy is equal to final kinetic energy plus final potential energy. And we want to find out the final velocity. Here you go. We know the initial velocity is equal to 0. Consequently, the initial kinetic energy must be 0 as well. Okay? At the bottom of the building, we can set up our potential energy equal to 0. And the potential energy, the initial potential energy, which is the potential energy at the top of the building, is going to be mgh. Okay? We want to find the final velocity. And the kinetic energy has the final velocity here inside, right? So we want to, basically, we want to find out if you calculate the final kinetic energy, we will be able to find out what is the final velocity. We do not know the mass, but we do not need to know the mass because the mass here cancels out. See that? And we are going to end up exactly the same result that we would get if you have used arguments of kinematics that we learned in kinematics. Here you go. Now we solve. And I'm going to put everything here on 2GH, right? 2GH. Take the square root of both sides. And we get a square root on the right side. And that's your final result. Using the kinematics equations, we find the same result, right? And how do we do that? We use the Torricelli equation. V square equal to V naught square plus 2A delta X. In this case, it's going to be delta Y. Just to prove that to you. All right? Okay, go. The initial velocity is 0. The delta Y is going to be H. Okay, actually it's going to be minus H. Delta Y is what? Delta Y is Y final minus Y initial, okay? Y final minus Y initial. The acceleration is going to be zero. It's going to be G. Y final is 0. Y initial is H. And now we can go, we don't need the 0 here, right? We can eliminate the 0. In the next step, let's see here. Yeah, we must have a minus G here. Here you go. Minus G, because the acceleration of gravity is downwards, right? This value here is A is equal to minus G. Okay, it's equal to minus G. And now negative G cancels out with negative H. That's the step by step. We're going to do that in the next step. GH, right? And we get exactly the same result we got before. V squared is 2GH. V is equal to 2G, square root of 2GH. Just like we got before for using arguments of conservation of energy. Elastic force. Let's do an example of elastic force. Here you go. A metal plate is attached to a spring of constant K. Let's see if I have an illustration for this one here. Doesn't look like I have. Okay, here you go. Yeah, I do have it. This one, here you go. A metal plate is attached to a spring of constant K. An object of mass M is compressed against the plate. It's compressed and doesn't become attached, okay? So it's gonna be something like that. Let's see, here you go. That's the plate, right? Let me, okay, here you go. Like that. Let me erase that. Okay, here you go. This spring is not compressed, okay? It's not compressed. The spring is the position of equilibrium. And to make it easier to understand, let's make the spring here, the plate, right? At the position of equilibrium. And now we get a mass and we attach. And we not attach, we don't attach, we put in contact with this plate, right? Let me, since the spring is on the position of equilibrium, there is no force whatsoever. Like that. Here you go. No force whatsoever. Then we just rest a mass to the plate. What else do? We compress the spring with the mass. So to compress the spring with the mass, we gotta do something like that, right? The plate is attached, but not the mass. Okay. Here you go. And now we do have displacement. Now we do have a force acting on the plate and consequently on the mass. Let's see here. I gotta get this guy a little bit more to the right, left. Here you go. Okay. The red vector is the displacement vector. This violet vector is the force vector. Okay. After compressing, we release the set. We release the set. Okay. And then what's going to happen? And assume that there is no friction, right? Assume there is no friction. No, the conservative forces is going to be equal to 0, right? So here you go. When I release this whole set is going to move to the right, including the plate and the mass as well. Playing the movie for you to see, right? It's very important to play the movie as the spring goes back to its initial position, both the displacement and the force ends up changing, right? The displacement becomes smaller, the force decreases as well. Okay, and here you go. A little bit later on, the mass going to be here, the position of the equilibrium. The plate that is attached to the spring is also going to be at the position of equilibrium. The force is going to be, the displacement is going to be 0, right? The displacement is going to be 0. And the force is going to be 0 as well. Like that. Here we go. There is no force vector here. But then, after the whole thing, let's see if I have the, yeah. At this very instant of time, just a little bit afterwards, the mass is going to detach from the spring, from the plate, the spring is going to be a little bit stretched, okay? But the velocity of the plate is going to be slightly smaller than the velocity of the mass. That's why the mass is going to detach from the plate of the spring, okay? There will be, can you picture that? Okay, there will be a little bit of force, but now the force is going to be in the other direction. This one, let's see here. Right here. The force is going to invert the direction, right? No longer is going to be zero. The displacement of the spring is going to become positive. Okay. The force is going to invert direction because now the spring is stretched, no longer compressed. Yeah. Yeah. Canvas sometime. Okay, let's see if I can. Oh, good. Exactly what I want. Gonna be like that. Okay. A little bit later, this plate is going to be I'm gonna put also a velocity vector here for the mass. Okay. The force on the mass is going to be zero because there is no more elastic force. And by the way, the surface is assumed to be frictionless. Okay, the force is assumed to be frictionless. A little bit later on, the mass is going to slide past, right? If we are talking about conservation of energy of the spring, this mass is going to end up, the plate is going to end up stretching the spring a little bit more, right? But now the mass is moving faster than the plate. That's why it detached from the plate. Okay? Initially, the mass is at rest and the spring was loaded, right? You release the spring, then the spring accelerates the mass. When the plate of the spring reaches the point position of equilibrium, the force is going to be the greatest, and so is the velocity of the plate. But when the plate of the spring go past the position of equilibrium, it starts to slow down because the elastic force now changed direction to the left. The mass that was not in contact, that's not attached to the plate, is then released from the plate, right? So let's play the movie. Here you go. You want to play the movie all over again? What? Okay, here you go. This one, let's see here. I don't want to. Okay, here you go. The movie starts here. The plate and the spring. The spring is in the position of equilibrium. Consequently, the force is going to be zero. I rest a mass on the plate. It's not attached. It's not physically attached, but just touching it. Don't forget the surface has no friction. I also compress the spring to add, when I compress the spring, I'm adding potential energy to the system, to the spring. I'm adding potential energy to the spring. And now there is this displacement to the left and a force to the right. That's why we have that negative sign, right? I release the mass. I release the mass and consequently the spring. And the spring starts accelerating the mass. Okay? The mass was at rest, but the spring was at rest, but then we added potential energy to the spring. When I release the set, the spring is going to be propelled by the spring, okay? Eventually, the force, the elastic force, goes to zero because the spring, the metal plate of the spring reaches that position of equilibrium in which the force is applied to the mass is zero. And this is also the point of maximum speed of the mass. At this point, the force, the elastic force, reverse direction because the plate passed the position of equilibrium. Because this force in the plate is now to the left side, this plate is going to slow down, whereas the mass is going to keep on going with that velocity, that maximum velocity it reaches at the position of equilibrium. Okay? The distance between the mass and the plate keep on increasing. Notice that velocity vector of the mass is the same, unlike the force, the elastic force, which is increasing. Okay? And what do we want to do? We want to know this velocity of the mass at the position of equilibrium. That's what we want to know. I can, let's see, yeah. Did you get the idea? Let's play the movie again. I don't think I need the other pictures. Let's see here. Let's see if I'm gonna need that. No, I don't need that. I can erase it. 1, 2, and 3. Okay, and 4. Okay. So that's how the movie plays. Play at a plate, spring at the position of equilibrium, elastic force 0. We place the mass in contact with the plate, compress the spring, spring releases. When we compress the spring, there is the displacement and there is also this elastic force to the right. Release the set, and the mass and the plate of the spring start accelerating. When it reaches the position of equilibrium, the force is going to be 0. The velocity of the mass is going to be maximum. Okay. And because there is no attachment between the mass and the plate of the spring, the mass is going to lose contact with the plate. As the spring slows down, as the velocity of the plate slows down due to the elastic force that changes direction. Okay. And I don't need that anymore. Let's see here. Yeah, I don't need that. I don't need that. I can erase that. Did you get the idea? I don't need that either. Yeah, I don't need that either. And then how do we solve this problem? Well, we want to find out the final velocity of the mass. We want to find the velocity of the mass right in here, this spot. And I'm going to need this as well. Here you go. The velocity vector. That's my final instant of time. That's my initial instant of time. Initial velocity is 0, but we do have some potential energy here. Potential energy equal to half kx squared. Okay? And writing here, the potential energy reduces to 0, but the mass now has this kinetic energy half mv squared. Got the idea? And I'm going to go. I'm going to write that down here. Let's see if I can get that. Will potential energy. Let's put that potential energy, right? Greater than 0. Elastic potential energy. And I can also write down that the kinetic energy is equal to 0 because the set is still at rest. Like that. And then when the mass loses contact with the plate, right here at this spot, potential energy becomes equal to 0, and the kinetic energy is going to be greater than 0. Okay? So we go ahead and use the work kinetic energy theorem in the format of the conservation of mechanical energy. Like that. And displays the amount x naught. See that? We have k and x naught. Initial kinetic energy is 0 because the mass is released from rest. But the initial potential energy is half k x naught square. Okay? The final potential energy is going to be 0. And the final kinetic energy is going to be, did I give a metal plate? Metal with attached to string? Oh yeah, an object of mass m. Here in this case, I gave you the mass, right? Kinetic energy is half mv final square. Zeros here disappear. No need to keep them in the equation. We cancel the half. Let's do the next step. We cancel the half. Mass in this case is not, doesn't cancel. And we pass the mass to the other side. And we take the square root of everything. All right, here you go. X naught square can be taken out of the square root. And that's what we get for the final velocity. This type of problem cannot be solved using forces. It can be solved, but it requires higher order mass, okay? It requires a calculus. That's the elastic force. Now let's do another one. Have you ever heard the spin launch? There's a company called the Spin Launch. Okay, Spin Launch Launcher Let's take a look at this spin launcher. Some people criticize them. Spin launch company is a company. Orbital launch system is a really crazy idea that they're located in Long Beach, California, Conant Street. And it's a really crazy idea, you know. I think it's an amazing idea. Many people criticize those guys. They think it's not gonna lead anywhere. What they're trying to do, they are using the kinetic energy of a payload to launch it into orbit. Okay, what you see right in here? Why spin launch? It's spin launch because you rotate the object in this huge facility here. Rotate faster and faster to achieve larger, higher and higher speeds. And if this speed is fast enough, you will be able to put an object in orbit more easily without spending fuel, but only electrical energy. Let's see, Spaceport America. Where is Spaceport America? It is a 33-meter suborbital accelerator in vacuum. Okay, what we have here is a vacuum inside this device to bring down, the idea is to bring down the air friction, okay? It's capable of launching test payloads from 800 to 5,000 miles per hour. 5,000 miles per hour is orbital speed. It's 8,000 kilometers per hour. Let's calculate that, 8,000, 5,000 miles per hour. So I suspect that's orbital speed. Let's take a look here. Let's do the math. 8,000 miles per hour, miles per hour, 8,000, 1, 2, 3, right? And then we got a kilometers per hour. You got to multiply 1.6 by 8,000. You get, okay. Now it's 12,000. Okay. Now, what about meters per second? Meters per second, we get divided by 1,000. 3. Let's put meters per hour first. Meters per hour. Miles per hour. Okay. It's not divided by 1,000, it's multiply it by 1,000. Format cell, number. Okay, what about meters per second? Now we divide by 3,600 and let's see what we get. Yeah, 3,000. Okay, 3.5 kilometers per second. Okay, kilometers per second. It's not orbital speed, by the way. Orbital speed is 8 kilometers per second. Just, yeah, almost 4. 3.5. Here you go. Orbital speed is twice that much. Okay, so that's what they do. They accelerate this guy at 3.5 kilometers per second. It's very fast. How many miles per second that is? Let's go back to our miles per second. Divide that by 1.6. 2.22 miles per second. So that's what those guys do, right? They rotate the object here inside faster and faster until they achieve 2.2 miles per second. When they achieve this high speed, there are ways of releasing the mass, so it goes through this through this cylinder, right? It's like a gun. It's like a gun that uses centripetal force. Payload from 800 to 5,000 miles per hour. Comprised of the key components needed for the orbital launch system. Okay, the suborbital accelerator is a critical stepping stone in spin launches past to orbit. And since then, the system has conducted regular test flights with a variety of vehicles and launch velocities. The system also offers testing capabilities to customers, and they supposedly do that in a much cheaper way. So you can reach orbit at a much lower cost. That's the whole idea. Let's see. Let's hear what this guy has to say.
Hi, my name is Dave Wren. I'm the Vice President of Technology for Spin Launch, and today we're at Spaceport America in southern New Mexico.
Okay, Spaceport America is in southern New Mexico. The company is located in Long Beach, but we have this huge facility in New Mexico where people can launch rockets and this payload here that they're launching. Okay, they call it Spaceport America. They're in New Mexico.
Suborbital flight test facility. Spin Launch is developing a new way to get to space. We're using electricity to accelerate vehicles up to high velocities to significantly reduce the amount of fuel, structures, and rocket systems that are required to enter orbit. Today's flight test will be flying at 1,200 miles per hour.
Okay, so here you go, it's just like a projectile launch, right? You launch your payload, it goes in a parabolic profile. But what they want to do, they want to orbit this object, right? So what they do, you must have some fuel here inside. Once the object reaches the highest point, you turn on the rocket engine, and it requires much less fuel to get into orbit.
Hour up to about 30,000 feet with our 3-meter long flight test vehicle.
So 30,000 feet. 30,000 feet is the height of airlines, right, that they fly.
We'll start by integrating the vehicle, pumping the system down, removing the atmosphere.
Let me see here. I want to see this one. Launch elevation angle, 86.7 degrees. See that? Maximum velocity, 536 meters per second. I got more than that. But of course, there is a range of velocities, right? Flight duration, 81.44 seconds. Apogee, 30,600 feet. All right. So
1,000 feet with our 3-meter long flight test vehicle. We'll start by integrating the vehicle, pumping the system down, removing the atmosphere from the vacuum chamber. And then when the subsystem checks are all good, we'll accelerate the system.
Mass accelerator, electrically powered, industrial grade component, high-speed airlock system holds vacuum. Okay. 50.4 meter high.
And conduct the flight.
So on launch day, my role involves overseeing all of the systems, the engineers that run them, and the build team, as well as ensuring safe operation of the entire system. A typical flight test first begins with...
Here you go. That's a flight test. Did you see the payload? Let's play it again.
Flight test.
Here you go. That's the payload. They're just testing it to see if the whole system works, right?
First begins with attaching the projectile.
That's the projectile.
We insert any test payloads for that day, attach the counterweight, seal off the vacuum system. Then we begin turning on all the support systems. We turn on the water systems for cooling. We turn on the vacuum systems to begin pumping down the chamber. Start heating and enabling all of the oil systems to run the drive. Once all systems are drained, we're down to vacuum pressure. Then we will turn on the drive system. We will bring the tether and the projectile up to idle speed. We run a diagnostics check. And then once we get clearance for the airspace for launch, we will then accelerate up to our target launch velocity, enable the exit system. Well, once all systems go green, we then launch.
Our release. Label countdown. Laboring countdown. 10, 9, 8, 7,
Countdown.
6, 5, 4, 3, 2, 1. Release.
Whoa. Okay. debris all over the place, right? Projectile going higher and higher.
You say control lights, enabling floodlights, pressure's on, taper down, water break, speed. All right. Good release.
So as you just saw, we had another successful test flight today. It was our 7th flight on this suborbital system. We launched at 1,200 miles per hour, which is the fastest speed to date that we've operated this system here in Spaceport America. We traveled up to about 30,000 feet. And after about a minute of flight, the flight test vehicle impacted the ground, and we actually dug it up, and it's ready for release.
Impacted the ground, and we dug it out, right? So the projectile comes so fast, right? So when it impact the ground, that they have to dig it out to recover it.
We're going to continue to push the envelope and provide more behind-the-scenes flight test footage as our test flight campaigns continue.
Here you go. That's the idea. The idea is to launch it so fast that it can go around the Earth and achieve orbital speed.
Hi, my name is David Wren. I'm the Vice President of Technology.
I've heard lots of criticism from those guys that it's not practical to do something like that. And but what this problem is all about, right? Here you go. Let's go back to our problem. Propels a payload at very high speed along the vertical direction. They can propel it in the vertical direction as well in the horizontal direction too, okay? Find the maximum height this projectile can achieve using arguments of conservation of energy. Consider that the height is high enough, so you have to use the universal law of gravitation, okay? The radius of the Earth is r and its mass is m. Neglect friction and other non-conservative forces. Okay, you have to, in this case, you cannot neglect friction. You have to, but you know, to make the problem easier, right? I asked you to neglect frictional force. And here is my payload being launched from the surface of the Earth. It has initial kinetic energy, but it also has some potential energy because this object is a given distance from the center of the Earth, okay? So it's going to climb the potential well, the gravitational potential well, we call it, until it reaches a maximum height. Okay, until it reaches a maximum height. We're playing the game, the movie, right? Initial velocity at the surface of the Earth as it climbs the potential gravitational wells, the speed decreases until it is momentarily at rest, where it reaches a height h. Okay, this height here I'm exaggerating. Okay, it doesn't climb that much high. It climbs only 30,000 feet. 30,000 feet is barely, you can barely see in this figure, in this illustration. 30,000 feet, you know, think about that. This is 6,000 kilometers, what you see here. 30,000 feet is only 10 kilometers, right? So 10 kilometers is not that much high, okay? It's just skimming the Earth's surface. So here is the final potential energy, the final kinetic energy, and here is the initial kinetic energy and initial potential energy. Okay, so let's solve this problem. Here you go. Initial potential energy plus initial kinetic energy is equal to final kinetic energy plus final potential energy. We already know that the final kinetic energy is going to be 0. Right, here you go. But we want to use the initial kinetic energy is going to be a spin launch propels a payload. I gotta put payload of mass. Let's see, do we need a mass? No, we do not need the mass. Yeah, we do not need MV not squared. Okay. And the potential energy in this case is the initial potential energy in this case is going to be mass of the projectile, mass of the Earth, gravitational R, and let's not forget the negative sign. Okay, the negative sign. I prefer to put this big G here on the outside. Wait a minute. We are talking about initial, right? Initial potential energy. So the radius is equal to the radius of the Earth. We have the same factor here, but don't forget it's the final potential energy. So that's gonna be radius of the Earth plus the height h. Can you see that the mass cancel out here? So you do not need the mass. We want find the height of the projectile when it's spin launched. Okay, mass cancel, mass cancel, mass cancel. We do not need the zero anymore. We can erase the parentheses, right? Here you go. We want to find h. Let's see how we're gonna do it. Can invert, right? We have to take can take the inverse. That's one way of doing it. Oh, we are almost our break, right? At our break here, 10:55. Let's finish that, and then we have our break. We're gonna take the inverse. Okay, inverse on both sides. When we take the inverse, this guy here changes. M goes downstairs. G goes downstairs. Oh, like that. In the next step, I am going to put everything under the same denominator. Oh. Let's see, what did I do? We go R and R. I gotta put 2 there downstairs, upstairs as well. Now that we have the same denominator, we can combine them in a single fraction minus big G to M. And we can invert the fraction. 2R goes upstairs. This one here goes downstairs. Let's see, we're gonna pass the GM to the other side. R plus H. Let me see, am I doing something wrong here? Looks like I forgot, oh yeah, I forgot the minus sign here, right? Nobody noticed that, did you folks? We must have a negative here. Okay, not this one, negative, negative, oops. Negative and negative. We can do the following. Instead of putting a negative here, I'm going to keep this one positive, and I transfer this minus sign to the other side, okay? When I transfer this minus sign to the other side, whatever is downstairs here change signs as well. Let's do this one for now. We go R goes to the other side and switches sign. And I'm going to change the sign here downstairs because I'm multiplying by minus 1. And that is the height that the projectile can reach with a given velocity. That's the radius of the Earth, that's the constant, gravitational constant, right? It is almost 11 o'clock right now. Do you have any questions about that? So let's have our break 11 a.m. To 11:15 a.m. Okay, and then I see you in the next 15 minutes. See you soon. Bye-bye. I'm back here. Let me get another student in. Here you go. Okay, so we did this one here. We did this example. Okay, so now you should have an idea how we can use this type of knowledge, right? To solve some problems. And this one, okay, that's not the one I want. I want the other one. Here you go. This one right here. Okay. And we are done. Conservation of mechanical energy. Okay, 1.5 let me do an example of non-conservative force. I already did an example of non-conservative force, right? No, not exactly, right? So let me see if I have a good example here of non-conservative forces. Well, the non-conservative force, all you have to do is to apply that equation, right? That has the work done by the non-conservative force. This one right in here, this equation here. All you have to do, okay? And what we are going to do now, okay, we're going to do cover power. This one we're going to skip. And last thing is power. And why do we define power, right? So we talked about work, the idea of work. And then there is also this idea, power. And why do we define power, right? There is a reason why we define power. And I'm gonna give you an example, a real life example, right? Example. Suppose you're in the market to buy a lift, to buy a crane. Suppose you're in the market to buy a crane to lift a very heavy load, 1,000 kilograms, let's say, to a height of 10 meters. Okay. So you have this 1,000 kilogram load, it's 1,000 kilogram mass, and you have to lift this load to a height of 10 meters, which requires an amount. Let's see here. Oh, it's not 100 joules. It's 100,000 joules, right? Here you go. The work done is going to be 1,000 kilograms times G, right? Which is 10 meters per second square times 10 meters. The work done by this lift, by this crane, should be mg, right? Times 10 meter high. And you need this crane to do a work that's going to be 100,000 joules. Okay. And then you go, let's say, you ask one salesman about the crane that can do this job, right? 100K joules. Let's see. And let's say the salesman tells you that it costs $10,000. Let's say $100,000, which gives you an average of $1 per joule. Okay. And then, oops. And then you go to another store, you talk to another salesman, and the second salesman tells you that he also has a crane that can do the same amount of work for half the price, $50,000 or 50 cents per joule. Okay. Now the question is that you have to ask yourself, is there a catch? You gotta ask yourself, is there a catch? Is there a catch here? Okay. Is there a catch for this? Well, before you make a decision, then you have to ask something else. However, before you make a decision, you have to ask something else. And the question you have to ask, what is the power of each crane? That's what you have to ask, okay? That he can lift a 1,000 kilogram load. Yeah, both of them can do it. But what about the power, right? What about the power? And the power, this idea of power is intimately connected with how fast, okay, a given machine can do a given amount of work, okay? Let me italicize here. That's what the idea of power is all about. Most likely, and then most likely the difference in price between those two cranes has to do with the power. Both cranes can perform the same amount of work, However, it is very possible that the second crane, is lower at performing this work compared to the other. And by lower, I mean, in other words, its power must be lower than the first crane, and most likely should be half. Okay. If the price is half, most likely should be the second crane must have a power that's half as much as the other one. So let's now define what power is, right? Like I said, so here you go. I'm going to write that down, something else too. Most likely the first crane must do the same amount of work in half the time, at least half of the time. Okay, so power is how fast you can perform a given amount of work. That's why we come up with this idea of power. And we can perform, here you go. So here you go. Now I have an example. The first crane performed the first job in 10 minutes, but the second crane, because it's cheaper, will perform the same amount of work in 20 minutes. And sometimes time in your job pays off, right? The less time that you spend doing a given amount of time, the more money you can make it. Okay, what's the power of each crane? Okay, we can come up with this type of example. The first crane performs the job of lifting 100,000, performing 100,000 joules of work in 10 minutes, and the second crane performed the same amount of work in 20 minutes. What's the power of each crane? Okay, so we gotta use that equation that you saw. First crane is not 110,000, right? It's 100,000 joules. MGH, 10 minutes. 10 minutes have 600 seconds. And what we end up getting is 166.67 joules per second. Okay, that's the unit of power. But the unit of power, this unit appears so frequently in physics that we give it a name. We call it watts. And I'm going to write that down here. Here you go. Brackets, square brackets, square brackets, square bracket here too. Square bracket for one, square bracket for the other, right? Square bracket for this one, square bracket for the other. Joules per second. And joules per second is the watt. The watt. Okay, abbreviated by the letter W. There's another way of writing the same equation. Okay, here you go. delta W over delta T. Don't forget that the amount of work is equal to the force times delta X, the distance traveled, assuming that the force exerted is constant. Delta X, but delta X divided by delta T is the velocity. Here, another way of writing down the power. The force that a machine exerts times the velocity that it is doing the work. Okay? And then we are done with chapter 6, work and energy. It is, and what I want to do right now, I want to start chapter 7 as well. Do you have any questions about that? Okay, the next chapter is the idea of linear momentum and its conservation. The sections that we have in the book are the following. Okay, chapter 7, and I'm going to do section 1. Here you go. Like that. Yeah, okay, good. We are going to skip the first section. Okay, I usually don't cover the impulse momentum theorem. I usually don't cover that. But I cover the rest. With the exception of center of mass, if we have time, we'll cover the center of mass, but everything else, okay? We'll cover the principle of conservation of linear momentum, collision in 1 dimension, collision in 2 dimensions, okay? Okay, so the idea of conservation of momentum is closely related to Newton's first and third laws. We can say that the idea of conservation is a consequence of Newton's first and third laws. You got it? And let's take a look more close. Let's take a more close look at this idea. Okay, so you already know that the net force applied to an object is mass times acceleration, right? And here what we have, mass times acceleration can also be spelled out as being mass times delta V over delta T. Okay, and I'm gonna just rewrite the last result here. Here you go. That's what we have, mv minus mv naught over delta T. Okay, if the net force is equal to 0, the net force applied to an object is equal to 0, something interesting happens to the above relation. And what's that? You know, what you have right in here is equal to 0, right? Not only what you have right in here is equal to 0, but also we can also say that what you see right in here is going to be equal to 0 as well. And look what we have. We have mass times final velocity minus my mass times initial velocity is equal to 0, which is the same to say, we can also say that what you have at the beginning, right, is equal to what you have at the end. Here you go. That is what you have at the beginning, and that is what you have at the end. This quantity that you see here on both sides, we call it linear momentum. Okay? The quantity that you see above, m times v, is called the linear momentum. And it is a vectorial quantity. Note that linear momentum is conserved. Whenever the net force applied to a system, linear momentum of a given system, right? Of a given system is conserved whenever the net force applied to this system is zero. So not only we have conservation of energy whenever there are only conservative forces, right? We also have conservation of momentum, linear momentum. Not only we have conservation of energy whenever there are only conservative forces, we also have conservation of linear momentum when the net force applied to a given system is zero. Is zero, okay? So here you go, let's the letter we usually give to momentum is the letter P. Here you go, P vector is mg. Initial linear momentum is mv naught. And now let's see how we can apply these ideas to solve problems, right? I'm gonna get some more illustrations here to linear momentum right in here. Linear momentum. Let's see if I want this one. Mass 1 is our system. Okay. Let's see, we have these two masses and they are going to interact with each other. And I have chosen mass number 1 to be my system. Okay. So you already know from experience, assume that there is no friction, frictionless surface. I'm gonna write that down here. Frictionless surface. This mass is moving, this mass is at rest. That's what V0 is all about, V0 is all about. Initial velocity of 1, initial velocity of 2. Okay. Since there is no, and here the instant just before we have a collision between those two objects, okay? Okay, anywhere between those two instants of time. Okay, let's play the movie again. Here you go. I'm following my mass number 1, right? Here you go. A time t equal to 0, a little bit later, and an instant just before the collision. An instant just before the collision, right? Okay, between this instant of time and this instant of time, you can see clearly that there is conservation of linear momentum for mass number 1, right? Because it has the initial velocity here, this spot didn't change until it's about to collide with the second mass. When it collides the second mass, what happens? This mass here is going to feel a force, which is going to be the collisional force. This mass is going to interact with the other mass, and it is going to propel the second mass. And the second mass is going to slow down the first mass. What you see right in here, those two forces, those two parallel forces, is nothing but Newton's third law of motion. Those two objects are interacting with each other, right? If object 1 applies a force in 2, the object 2 must apply a force that's equal in magnitude and opposite in direction. Okay? if those two objects somehow manage to stick to each other, they're going to move in tandem to the right side, okay? And that's possible to happen. This type of collision is called the inelastic collision. But you can see clearly that between this instant of time and this instant of time, you do have conservation of linear momentum for mass number one alone. But between this instant of time and this other instant of time, linear momentum is not conserved. Linear momentum is not conserved for mass number one, okay? Because the whole system changes its speed. So bring but there is a smart way of looking into that so we can solve problems more easily. Okay? It's just a matter of choosing your system properly. I chose my system as being mass number one. Momentum was not conserved after the collision. But if I do something else, if I choose both mass number one and mass two, something else is going to come out. Something else surprising is going to come out of this exercise. Look what's going to happen. Okay? Mass number one is approaching mass number two, and now mass number one and mass number two, they are part of a single system. So much that I put this box around here, right? To prove to you that they are a single system, have chosen them to be a single system. Mass number one is approaching mass number two, right? Just before collision. And at the moment of collision, you are going to have this force applied to our system. The two masses make up a single system. I have defined in this way. And look what's happening here to the net force of the single system. The net force being applied to the single system is going to be F21 plus F12. Because they have the same magnitude but opposite directions, the net force applied to this whole system is going to be 0. Okay? So this tells me that if I choose my system properly as being the two masses that are interacting with one another, the linear momentum will conserve, okay? That's the whole trick. That's the whole secret of conservation of linear momentum. Is by choosing, you have to choose properly your system. Okay? So you go consider, I'm going to document everything that I told you here before, right? Consider a single mass alone moving over a frictionless surface with constant velocity. Constant velocity. Okay? In this case, the net force must be 0. And because the mass is moving, and because the net and because of that, right? Because of that, we must have conservation of linear momentum. Linear momentum. Now consider the case of two masses colliding with each other. They are both on a horizontal surface, horizontal frictionless surface. the first mass is moving with the initial velocity V01, and the second one is initially at rest, right? V02 is equal to 0. V02 is equal to 0. We can say that momentum of the first mass alone is conserved only within a time interval before the collision happens. However, momentum is not conserved for this first mass because after the collision, not after the collision, because at the moment of collision, the net force applied to mass 1 is different of 0, right? The same thing can be said about mass number 2. If we choose, right, mass number 2 as being our system, its momentum will be conserved only just before the collision. After the collision, momentum is not going to be conserved. Now, choose mass 1 and 2 as being our system. In this case, there will be conservation of linear momentum because the net force is equal to 0 by virtue of Newton's third law of motion. Okay. Okay. I'm going to copy and paste something else that I wrote before, okay, that explain more detail what I have just written there. Here you go. I'm just timing exactly, in a detailed fashion of object number 1 moving the other one at rest, right? So we are considering object number 1 as the system, our system, between time t equal to 0 and just before the collision, this object will be propagating the velocity v01 between 0 and t1, right? Between 0 and t1, momentum is conserved in the first object, but not after the collision. But if you choose the system as being the 2 objects simultaneously, the situation changes considerably. And now we can come up with an example. Let's see, I think we can go, before the example, let's have our break again. Here you go. Break. 11:50 a.m. to 12:05 a.m. p.m., right? Let's take our break now. And I see you in 15 minutes, okay? Thank you. I'm back here. Let's see. Yeah. Great. Okay, now we can come up with that example so we can have a better understanding of how this concept of conservation of linear momentum applies, okay? So consider an elastic collision between two objects of mass m, okay? They have the same mass. The first object has a known velocity and the second object is at rest. Find the velocities of both objects after the collision. Okay, now what's an inelastic collision, right? Inelastic collision is a collision by which both objects stick to each other after the collision. After the collision. That's the easiest type. This problem that you're seeing here is the easiest one that you're going to see out there in terms of linear momentum. Okay, two objects undergoing an inelastic collision and they have the same mass. That's the simplest type of collision that you're going to see. How can you? It's possible to duplicate an inelastic collision in real life. Okay, this is not an idea out there. Okay, it is possible. Inelastic collisions do exist in real life. One way of reproducing an inelastic collision is by attaching a piece of Velcro in each object. When they collide, the Velcro is going to keep them stuck to each other. Okay? Assume the surface, let's say, assume that the two objects are moving over a frictionless surface. Okay, assume the two objects are moving over a frictionless surface. And now, right in here, no, not this one, right? This one is work. It's the other work, that other one here. Here is the situation that you already saw. One object moving towards the other one. First one is at rest. They collide. Because the system is considered to be in the two objects, the net force applied to the system is going to be 0. And then we have this final velocity. We want to find out the final velocity of the set. Okay, here we go. Let's see. Here's another one. Okay, this is another example that we're going to do later on. So here you go. Here you go. That's the initial time. Okay, so we go ahead and apply the condition of conservation of linear momentum. Initial moment is equal to final momentum. But then how do we write down the initial momentum, right? Well, the initial momentum is going to be the sum of the two momenta. Momentum of the first one, initial momentum of the second one. Okay? M1 times V01 plus M2 times V02. And the final momentum is going to be M1 V final 1 plus M2 V final 2. We do not know V final 1. We do not know V final 2, right? But because now we're going to apply the knowledge, right, that the two masses are the same. The condition, right, of the problem, two masses are the same. M1 equal to M2, and it's going to be equal to M. Okay, here you go, M, M, M. We still do not know V final 1 nor V final 2, right? We are going to apply also that the initial velocity of the second object is 0. Okay, so initial momentum is going to be just mv01. And we are going to apply another important condition that's related to the inelastic collision. Because it is an inelastic collision, the final velocity of the first object must be equal to the initial velocity, to the final velocity of the second object. And now we can simplify the notation and just write down this final velocity as being v. Okay? That's an important thing about collision, inelastic collisions. In an inelastic collision, the final velocity of the first object will be equal to the final velocity of the second object. And now our equations become even more simplified. Instead of having 2 unknowns, now we have just 1 unknown, right? Final velocity of 1 becomes final velocity. Final velocity of 2 becomes final velocity. We go another step. Oh, let's see. Initial velocity of 2 is 0, right? So I can, from here, we can go another step. 2 equations, 2 vectorial equations. You go. And now we have just 1 unknown, which is the final velocity. We are going to apply the linear momentum conservation. Okay, applying that. Go. MV01 to MV. What is bold-faced is what we do not know. Mass cancel out with mass. Okay, here you go. I can erase it. And look, let's see here what's going on. Okay. We do not know this V, right? And then we finally get that our final velocity of the system is going to be half of V01. Hiccup. Half of V01. But just by applying this simple, like I said, this is the simplest example you're going to see it. Example of, let me give you a list of examples of conservation of momentum. That obvious case, right? Of a single object moving over a frictionless surface. In this case, the net force is 0 and the velocity is constant, so the initial momentum is equal to the final momentum. This is the obvious case. What's not so obvious is this case that I just presented to you. System of 2 objects which are colliding. The momentum is conserved just before the collision and at t just after the collision. Momentum is conserved for the following reasons. During the collision, object 1 interacts with object 2, right? More specifically, object 1 applies a force of F12 to object 2. Conversely, and according to Newton's third law of motion, object 2 must apply a force of F21 equal to minus F12. Consequently, the net force applied to our system, and by our system I mean the both masses, is going to be F21 plus F12. F21 plus F12 is actually F21 minus F21, which is equal to 0. Consequently, momentum must be conserved. Example 1 is the case of a single object. Is the case of two objects of same mass, one moving the other at rest. This is the simplest example you may end up solving. It's also a 1D collision problem. It is also a 1D and an 1D collision problem. Now we are going to do example 2, two objects of different masses. Inelastic collision. Two objects of different masses, M1 and M2. V02 is 0. V01 is none. Go. V01 is none, and V02 is 0. Okay, find their final speed. Again, consider the surface frictionless. Here we go. That is the next set of slides. Here we go. Let's say M1 has a larger mass, right? So I drew it larger. It's moving towards M2. Here we go. It's going to collide. They're going to interact with each other. Even though M1 is a larger mass, the forces are still going to be the same. It's going to be an inelastic collision, and the whole set is going to move with a final velocity. It's the same velocity for one. Velocity of one is the same as velocity of two. Okay? So momentum here at this initial instant of time must be equal to momentum at this final instant of time. We're going to do that all over again. Not much different than before. Okay, here we go. Solution. We got initial momentum is equal to final momentum. Initial momentum is the sum of the two initial momenta, P01 plus P02. Final momentum is equal to the sum of the two momenta separately. Because it's an inelastic collision, final velocity of one must be equal to final velocity of two. Okay. And we end up with this relation. Now it's M1 plus M2. It's no longer 2M, right? Because the M1 is different of M2. The relationship is, let's see what I want to do. The relationship, oh gosh. Relationship in question is this one here. And then we solve for the unknown quantity, which is the final velocity. Here you go. M1 over M1 plus M2. So, and this, if M1 equal to M2, we must get the same result we got in example 1, right? Let's see if it if it works. Let's see if it actually works. This is just a test, a little test that you can do for this final result. Here you go, M1 equal to M2. Let's put it equal to M. Okay, here you go. M. Okay, downstairs becomes 2M, right? And then M cancels out with M. And we get exactly what we got before. We get exactly what we got before. $12.21. Any question? Am I missing any question here from you? Here you go. Real life examples of inelastic collision. Collision between two objects that have Velcro attached to them. You already know that. And the collision between two cars, okay? Nowadays, cars are engineered to undergo an inelastic collision to preserve the lives of passengers. In this case, the frame of the car is wrecked, but the lives of the passengers are spared. The frame of the car absorbs most of the force of the impact. Notice that new cars get wrecked more easily than the older ones. But this is done to preserve the lives of the passengers, okay? It's far cheaper to fix a car than to fix a human being. But okay, so that's what we have for, there are many other problems with inelastic collision that you can solve, but those are the two basic ones. You can extend this process, this technique that I did for those two simple problems to other ones that are more difficult, right? Okay, more difficult to do. And in addition, so we have in an inelastic collision, two objects are separated initially, and then at the end they are combined, right? Two objects at the beginning. We can say that we have two objects at the beginning and a single object at the end, a single larger object at the end, right? That's what the inelastic collision is all about. Since they are moving together, they can be considered as a single object. Then there is another type of problem. Then there is another type of problem that is the inverse of an inelastic collision. This type of problem, I like to refer them as explosions, okay? And what I mean by inverse, I really mean that if in elastic collision we have initially two objects and at the end we have only one, for the case of an explosion, initially we have one object, and after the explosion we have two or more objects. Okay. And the situation can be illustrated like that. Here you go. Can be like a gun and a bullet. Okay. They are considered my system. In this case, there is a process in which, let's say, a gunpowder is activated, or can be even a spring. The objects are kept loaded, the objects are joined by a spring that's loaded, and somehow there is a trigger that releases the spring, and the two objects fly away. Okay? That's one way of looking at that. One applies a force in two applies a force in one, and then they fly away from each other. That's what I call an explosion. Final velocity of one, final velocity of two. And the same principle can be used in this case. That's going to be example 3. Two objects of the same mass initially stuck together and at rest. Can be a gun and a bullet, for instance. Somehow internal force is activated. Can be the gunpowder that's triggered. And the two objects fly apart. Find the relation between their final velocities. You cannot find the exact value of the velocity with this information that I gave to you, but you can find the relation, the ratio. Find the ratio, right, between their final velocity. Let's see, final velocity of 1 divided by, let's see here. Final velocity of 1 divided by final velocity of 2, okay? Solution. Initial momentum is equal to final momentum, but the initial momentum must be 0 because they are both at rest, right? If the initial momentum is 0, the final momentum must be 0 as well. Here you go. And let's not forget that the final momentum is going to be the final momentum of the first object plus the final momentum of the second object. We go ahead and write down, spell out, right, what final moment of 1 is all about and what final moment of 2 is all about. FVF1, FVF2. MFVF1 plus MVF2. We can put the mass in evidence. And because the mass is different of 0, we can go the next step and say that V final of 1 plus V final of 2 is 0. Okay? And that is the relationship we get between those two final velocities. They have exactly the same magnitude, but opposite direction. Consequently, their ratio, okay, should be equal to -1. I'll put this way here, VF1, VF2. Remember, we have to get the scalar division, not the vectorial division, right? Vectorial division is not accepted. Here you go. The two objects end up with the same speed because they have the same mass. If they had different masses, then the speed would be different. Okay, we can do that. Let's do that. Two objects of different masses. Now one has twice the mass of the other. Okay, and then you're going to see what's going to happen. Two objects end up. Here you go. Example. I'm going to put the 3 prime. Okay, two objects of different masses. M1 equal to M and M2 equal to 2M. Okay, one has twice the mass of the other. Like that. Somehow an internal force is activated. Can be the gunpowder, for instance, of the bullet gun of the gun bullet combination. For instance. Now I find the ratio between their final velocities. Now here we go. It's exactly the same step by step. The only difference now is going to be the masses. P naught equal to P final. P final equal to 0. And here I'm going to add M1 and M2, right? One mass is larger than the other. Okay, M2 is larger than M1. It's twice M1. Here we're going to have M. Here we are going to have 2M. We want to know the ratio between them. But before we get the ratio, we have to put M in evidence. Okay, got like that. Oh, I meant, oh, this thing is annoying. Got this M, right, can be taken out from my equation. And then because the first mass is lighter than the second one, its final velocity is going to be larger. Final speed is going to be larger. Okay? Changing that change this notation from vectorial to scalar. Like that. Like that. What do we get? We get that this ratio now is going to be -2. What does it tell? It tells that the speed of the first of mass 1 is going to be twice the speed of the second one. 12:35. We have 15 more minutes to go. Like I said, because I did not tell you anything about the total internal energy of the gunpowder, we could not calculate the numerical value of the velocity, right? However, if I tell you what is the internal energy that provides, that allows, right, the two masses to move away from each other, we will be able to find an equation for the final velocity. How is that? And that's what the next problem is all about. Refer to problem example number 3. Refer to example number 3. Assume that the not the potential energy, because it's not necessarily a conservative force. Assume that the internal energy of the gunpowder before the explosion is U naught. Assume the following. 2 assumptions here. 1, the internal energy of the gunpowder before is N. 2, 100% of this energy is converted into kinetic energy after it is ignited. It is ignited. So what do you want to do? Find the final velocity in terms of U naught, okay? In this case, okay? Now we will, in addition of having, in this case, in addition to conservation of momentum, we will also have conservation of energy. That's how we solve this problem. So now instead of just one equation for conservation of momentum, we're going to have now 2 equations. One vectorial equation for conservation of momentum and another scalar equation for conservation of energy. Okay? So we have, I call that internal energy. It's not potential energy, okay? It's internal energy. So the kinetic energy plus the internal energy is going to be equal to the initial kinetic energy plus initial internal energy is going to be equal to final kinetic energy plus final internal energy. Since the 2 masses are at rest, okay, the initial kinetic energy is going to be 0. Since you used up all the internal energy, so we can, the internal energy of the gunpowder is U naught. We can put another one. 2, you use up completely. No, there's one more. There's one more assumption here. Used up completely the internal energy after the explosion. And 3. So this internal energy disappeared after the ignition. I am going to, let's see here. that here is going to be 0, right? Because the object is initially at rest. Here is going to be, they're the same math. Yeah, they're the same math. We're doing the same math here. V01 makes things easier, right? No, it should be final, not. V vector final 2. Here, let's see, this one disappeared. This one also disappeared. But here we must have final kinetic energy of 1 plus final kinetic energy of 2. Right? Kinetic energy of 1 is half mv final 1 square. Final kinetic energy of 2. Okay, and I'm going to emphasize the fact that we do not know V final 1 and V final 2. Okay? I'm going to emphasize this fact. One more step here. You know, V final of 1 is going to be minus V final of 2. Nothing changed in the conservation of momentum, right? And I'm going to simplify my notation. Yep. Put equal to V. And now that we have a relation between V final 1 and V final 2, we can, use it right in here. V final 1 is V. V final 2 is minus V. When we square the negative of V, the minus sign disappears, right? And we have mv final squared. And we are about to find out the exact value of the final velocity. It's going to be, you go. V final square root. So we were able to find the velocity just by using the value of the internal energy of the gunpowder. This type of problem is a little bit more challenging than the inelastic collision, Because now we have a system of two equations. One is on conservation of linear momentum, and the other one uses conservation of energy. See, compare this. Here you go. Compare this problem here, right? In the case of the explosion. With this other problem here not this one, sorry. Is the other problem here, let's see, the case of inelastic collision. In this case, we have just one single vectorial equation. Here we have one vectorial equation and one scalar equation. That's what I meant here. It's a little bit more challenging, mathematically speaking. Mathematically speaking, here you go. This problem is a little bit more challenging than the inelastic collision one because we have an additional equation. Instead of system of one vectorial equation, we have a system of one vectorial equation plus a scalar equation. 12:47, 3 more minutes to go. Okay, so we're running out of time here. Let me just put a real life example of an explosion, right? A gun and a bullet being fired, a cannon and a cannonball. Okay, and so far we have looked at these two types of collision so far. The second one is not exactly a collision, right? It's an explosion. And there is one more type of a collision that we have to worry about, and we are going to cover it next time. And the totally elastic collision. Okay? Totally elastic collision. In this case, energy is conserved. And then we have also another type of collision, that partially elastic collision. Energy is not conserved. And by the way, in the case of inelastic collision, energy is not conserved, okay? Oh, not just energy, but mechanical energy. Mechanical energy is not conserved. That's what I meant here. Here I meant mechanical energy. Here I meant mechanical energy. In this case, mechanical energy is not conserved either, because we have this internal energy that's not potential. Okay, and what we're going to do next time is going to be the totally elastic collision. That's mathematically is more challenging. Okay, and if you do not have any questions, we can stop here, and I'll be here for the office hours. Okay, so see you the day after tomorrow.
Thank you, Professor.
Welcome. Let's see. Mr. Vego.
Professor,
Yes,
can I get help with lab number 3?
sure. Okay, let me close this window here. Stop